I'm Sruba Seshadri. I am actually account technical manager for Cadence. I cover Southwest and Southern California. I used to be an applications engineer, and before that I was actually the product engineer for Spectre RF. In the early days of Spectre RF, when we started with Ken Kundert, it was just 3 of us, and and then it became a huge product and golden standard for simulation in RF. So today we will talk about how to use the RF analyses in Spectre using Specter X and also APS. So last week, what I did was I talked about the simulation technologies, APS and Specter X, and did not really focus on RF analysis. It was mainly for transient and general guidelines for using APS and Specter X, and what's the difference between, the main differences between these two technologies. But today we will talk about the RF analyses, focus on the RF analyses like PSS or harmonic balance. How do you deal with convergence issues? How do you improve runtime? How do you improve performance without sacrificing accuracy? Do's and don'ts, and kind of a lot of that. So we will go through a few slides, and then what I'm going to do is try and use the button that you showed me and get this thing off and try to write on the whiteboard, because once we do that, I think the remaining slides will become a lot more obvious. And I have about 100 slides. We will not go through that, but I wanted to create a deck that is very comprehensive. So we will not go through all of them. However, once we go through the kind of the lay of the land by kind of writing on the whiteboard, and then go through the remaining slides, or as many as we can get through, I think it will make a lot more sense, even if we don't go through all the slides. Does that make sense? Okay. So let's go through a few, and then at some point I'm going to stop and try to give like an idea of what are the RF analyses and what are some of the things to look out for. What are some of these analyses more sensitive to, in terms of when you vary something, what does it mean to PSS and what does it mean to HB, at least for Cadence, for Spectre RF. So for all our simulation technologies, accuracy is all we mainly care about. It's accuracy, accuracy, accuracy. And we always try to not sacrifice any accuracy just to get performance. So it's a trade-off, and we are going to talk about all of these trade-off methods and what you can live with and how to achieve your goal, basically, how to achieve your accuracy requirements and get the best performance out of our simulator. So these slides I'm going to send over, so to your professors, and then I'm sure they'll send it over to you guys. So last session we started with this. This is actually gives the entire big picture. So we have the basic Spectre umbrella, and we talked about Specter X last time. We talked about APS last time. Today we will talk about Spectre RF. So don't think about Spectre RF as being a very separate simulator from APS or Specter X, because the underlying technology is APS or Specter X, and the RF is more for licensing and packaging, but what it mainly means is the high frequency analysis capabilities like PSS or harmonic balance or envelope, and the small signal analyses that go with them. So so basically, if you do not have the Spectre RF license, then you're not going to be able to run those analyses. That's all it means. But technology-wise, assumptions-wise, it's all the same basic infrastructure. So again, if you have a netlist that works with regular APS, that works with Specter X, it will work with the RF analyses. So PDK-wise, there should never be an issue. And of course, there are convergence issues, there are performance, all of those things, which is dealt with differently in the RF analyses, which we will focus on today. So Actually, you had asked me that question. Should we, for some reason, hold off on using the latest versions of Spectre when you're using a certain PDK? For Cadence, no. But if your foundry says, you know, we are pretty sure that this process node is not going to work well with the latest Virtuoso for some reason, that's a whole different issue. But from our perspective, we do not think you should actually stay in an older version of Spectre. We think you should always use the latest and greatest versions of Spectre. So so you can run these RF analyses using high performance simulator. And when you say high performance simulation, you'll get buttons in Explorer or Assembler. One is APS, one is Specter X, then there is Spectre FX, and so on. So you could choose APS or Specter X. Never use vanilla Spectre, because when you use regular Spectre, it's definitely not conducive for RF analysis. It may be conducive for running TRAN for a 10 to 15 transistor netlist. So, we'll talk about the error presets in APS and how they kind of map to the preset options with Specter X, and also talk a little bit about XDP, which is the distributed processing that greatly improves performance and capacity of harmonic balance simulation. But one thing to keep in mind is XDP is not available for PSS and some of the other analyses. I have a slide that lists. Yes?
Is QPSS not a part of Spectre RF?
Yes, it is. It is. So PSS, HB, QPSS, and envelope. These are the large signal analyses that are RF, and then there are small signal analyses that go under it. Yeah. So accuracy. In case of APS-RF, how do you determine accuracy? It's using error presets, moderate, conservative, or liberal. And for RF analyses, we never suggest liberal. Either use moderate or conservative. And for XRF, if you have chosen Specter X as your high performance simulator, and then you set up your RF analyses, always start with AX, and if you need more accuracy, go to CX, and if you think lesser accuracy will work, then go to MX, but usually start with the AX mode of Specter X. I talked about it in the last session, but I see a lot of new faces, so I'm glad some of these slides actually will be a repeat, so I won't really focus on that, but it's there for, referring to later. And then another thing I'm kind of pointing out only the main things in the slide, so the rest you can read for yourself. So one thing I talked about multiple times is plus APS. In order to speed up your transient simulation in APS, I said, well, you can use plus APS, which will make the simulator take bigger time steps, bigger chunks of time. And that way you can speed up your simulation, like for ADCs or PLLs. However, if you are doing an RF simulation, like PSS or HB or QPSS or envelope, never enable plus APS. It will actually, I don't think it will cause any inaccuracy. What it will do is it will ignore. It will just not do anything. So, but it's just best. The recommendation is never to enable plus APS. So when we talk about performance, we mean simulation time. When we talk about accuracy, we of course mean the circuit measurements that you are looking for. And then when to use XRF, Specter X RF, and when to use APS-RF. So when you have advanced nodes, like we have a lot of customers that are designing in 16, 7, 5, now 3. So when you have advanced nodes and then your pre-layout designs are large and post-layouts are huge, and in those situations, I would always say use Specter X as your high-performance simulation engine and then set up the RF analysis. Use XRF. And that will really not only improve speed, but it is also going to reduce your memory. And that makes a huge difference for RF analysis. And when do you use APS-RF? When your APS simulation takes, say, an hour or hour and a half, if you use XRF, how much will you improve it? Maybe, bring it down by 10, 20 minutes, maybe it won't make a big difference. But when you have an APS simulation that is 2 hours or more, then using Specter X, XRF can really, really improve performance, especially in advanced nodes. So this is, mainly the main reason for using Specter X is to deal with the capacity and also to be able to get better performance when APS takes a very long time to simulate. So these are some things that you won't find in a user guide. So these are things we kind of put together, which I think are good cheat sheets. So my colleague actually wrote there, resist the temptation to adjust these default settings. We truly mean it. Do resist the temptation to play with these settings. So what happens is, when you can go into your Unix prompt and say Spectre-H space PSS or Spectre-H space HB or something like that. And when you do that, you'll get a lot of information, but towards the end, you will actually get this table. What does it actually mean, for a driven circuit? For error preset of liberal, moderate, and conservative, you choose it from the form, but what does it actually mean? What it means is, this is the set of default parameters that the simulator uses to converge or to come to a steady state operating point. So what is for liberal? Reltol is 1e minus 3. For conservative, 1e minus 4. What is the rel ref? What is the integration method? LT ratio, steady ratio, max step. So all of these make each of these buckets. This is for driven circuits, this is for autonomous circuits, and so on. So when you choose an accuracy default of conservative, moderate, or liberal, this is basically what we use. So what we are trying to get at is, suppose you have a driven circuit and you think, oh, I need a lot of accuracy, I'm going to go to 1e minus 5. I should just be really careful and do something. So don't take those rash decisions unless you're absolutely sure of what you're doing, because what you'll do is, Spectre actually is very focused on accuracy. So do not use the parameters if you have a different vendor simulator, any vendor other than any simulator other than Spectre. If you are used to using, say, 1e minus 5 or 1e minus 6, don't feel the need to use the same value from someone else's simulator into Spectre, because the way the defaults are set, you get that level of accuracy with actually 1e minus 4 and everything else set the way it is as a default. So do not feel the need to think that, oh, someone else used 1e minus 6 in some other simulator, I should go ahead and at least go up to 1e minus 5. You are just going to make the simulator extremely slow with no gain at all in accuracy, because the conservative for Spectre is really golden with the defaults that it has. So unless there is a very valid reason, do not play around with these default settings. And this reference is a good reference to know. So we just talked about this review of the guidelines for APS. So for RF, never use liberal, always use conservative or moderate. And I would say, don't think because it's RF, I have to use conservative in APS. I'm talking APS here because there is no conservative, moderate, and liberal for Spectre X. So here, the thing is, when you actually go to very low power sweeps, those are the times when you absolutely need conservative. Other than that, you may even be able to get away with moderate. So see what your design is, what your test bench is, and what your measurements are. For the same test bench, for different measurements, you may need either conservative or you might get away with moderate. So one thing I want to talk about is, okay, let's talk about Specter X, and then when we go to the analysis portion, that's when I think I'll try to write on the whiteboard and try and get it more interactive. Then maybe I'd love for you guys to ask me questions so we can go deeper into how certain parameters affect HB more than PSS, which will make it clear on which one you should use. So one of the things I've always been asked is, you guys give us 5 ways of doing noise. Which one should I use? There is P noise, there is QP noise, there is HB noise, there is transient noise, and there is P noise, right? I mean, there is 5 ways of doing it. Which one should I use? So that is kind of a wrong way to start thinking. Think about, what is my design? Think about, do I have, again, I digress from this slide. I'm just kind of giving a basic idea of Spectre RF. So think about, what is my design like? Do I have 1 large tone? Do I have 2 large tones? Do I have more than 2 large tones? Are they coperiodic? Think about those things. Are they sinusoidal or are they square wave? Think about that, because that is going to determine whether you're going to use PSS, or you're going to use harmonic balance, or you're going to use QPSS. Once you figured that part out, then if you're going to do small signal noise after that, you have only one choice. If you have chosen to use HB, of course, when you go to small signal noise, you'll use HB noise. You don't have any other way of doing it, because for any small signal analysis to be performed, first, the large signal steady state operating point has to be calculated. So if you do P noise, you would have had to finish PSS. If you do HB noise, you have to do HB, and so on. So anyway, I just thought we'd talk about that and then go into this slide. So as I said, for using RF analyses with Specter X, we said you could use it in production starting Spectre 20.1. If you're using transient, 19.1 is okay, but for RF, 20.1 and beyond. So 21.1 is what we have now, and use them with the latest in IC 618 or IC ADV 20.1. These are the virtuoso versions, 618 or 20.1, and the Spectre version is 20.1 or 21.1, whatever. And what are the presets that when you use Specter X, previous slides I talked about APS, error presets, conservative, moderate, liberal, but when you use Specter X, there are 5 settings I talked about last week: CX, AX, MX, LX, and VX. And for RF, start with AX. If you need more accuracy, go to CX. If you think I want more performance, accuracy seems to be fine, try MX. Never use LX or VX. LX is like the liberal mode of APS. You would never use liberal for RF. Similarly, do not use LX or the even more aggressive VX. No. And then so these are just the different analysis options, the command line options. We'll talk in detail in the next few slides instead of me talking about them here. So again, I talked last time about multi-threading. So you can use multi-threading or multi-core, where you can use multi-threading in APS or Specter X, just like I said before. When you use multi-threading, you can say I want 8 threads or 16 threads for post layout, or it's a small pre-layout design, I can do with 4 threads. Or if you actually have a job distribution policy where you use the form, use LSF, you can put LSF over there, and the same goes for APS or Specter X. It doesn't matter which engine you have chosen. And these reference to articles is very important. Actually, I have not done the hard work. A colleague of mine actually put a lot of these details together, and these are, if you go to support.cadence.com and you actually type up this article number, you will get a lot of additional information on multi-threading, multi-core, and all of that. And these articles have been written by application engineers, experts, so they are very helpful. So again, this is kind of all of this put together in a nutshell. So when you have APS, we have 3 buckets, which I talked about, the default settings: conservative, moderate, and liberal. When you use Specter X, you have 5: CX, AX, MX, LX, and VX. If you think about, it's not a direct mapping, but if you think about what kind of accuracy, if I want similar accuracy as moderate and I'm using Specter X, what should I use? MX would kind of be like moderate. CX would kind of be like conservative. But in in APS, there was no AX, but AX is really the sweet spot for RF. So when you're using Specter X and RF analysis, start with AX, and more accuracy, go left, less accuracy but more speed, go right, and never use LX or VX. And in APS, like I said before, you have to deliberately enable post layout to be able to get post layout optimization. And for post layout netlists, always enable post layout in APS. And I will kind of talk about what is the best option for post layout optimization for RF analyses, which is HPA. We have slides that will talk about that. But for Specter X, you do not actually have to explicitly say, I want post layout optimization. If you have chosen AX as your preset, for post layout preset, post layout optimization, we will by default choose AX for you. If you want to choose something else, you can do it on your own. So I always tend to go ahead of my slide, sorry about that. So this is kind of what I just talked about. So you have chosen Specter X. These are the 5 settings. Suppose you chose AX because you're doing RF, and you can choose multi-threading, which is the most common. You can use auto, then you let Spectre decide, should I take 8 threads, 16 threads, 4 threads. But if you want to determine yourself, go to manual and ask for the number of threads. Suppose you have a post layout netlist and you think, oh, I need 16 threads, and you put 16, but Spectre decides that you do not need 16 threads, you can actually do it 8. It will use only 8, and the way you find out is in the log file, it will say only 8 threads enabled. It's not going to give you the 16 that you asked for because you don't need it. Any questions on the accuracy settings? So this is again, so I talked about you have the presets, and then you have the, in Specter X, you are not required to explicitly set a value for parasitic optimization. You have to set something here, one of these 5. Suppose you've chosen AX. We will choose parasitic optimization value of AX, but that is not written in stone. If you want to change that, if you think that I have this design where my parasitics have very little bearing on the accuracy of my results, I will keep preset as AX, but I want really aggressive RC reduction, I will use parasitic optimization of LX. You can do that. Or if you think that I do not want my parasitics my circuit is extremely sensitive to my parasitics, so I want hardly any to be cut. So you can choose CX here and AX there. You can do it explicitly, but if you forget, which people do with APS, if you forget, then it's not like you will run without parasitic optimization. You'll always get a handshake. And there is this thing called preset override. Again, normally we say do not touch this, but if you are very particular about maintaining a parameter from your APS netlist, like like Reltol or the integration method or something, you can actually do preset override and put it here, but we definitely do not recommend. If there is a reason, you could do it, and then Specter X will actually be forced to use that value for that particular parameter, but keep in mind that might affect the performance of Specter X. Again, I guess I went ahead of myself, but this is what happens when you have chosen a preset. We by default give you the corresponding same thing for parasitic optimization, but suppose you, like I said, suppose you feel that I need to go off diagonal, and then you can actually pair AX with MX for post layout or AX with CX for post layout. You could go either way if you know how your design behaves. What's the best for performance and accuracy? So here I want to talk about, okay, let's go with the picture. I am better with pictures. So in APS, when you do post layout when you want to do post layout optimization, then there are three options: default, HPA, and UPA. For RF designs, always use HPA. If you are using APS post layout for RF designs, always use HPA, and this is how the form looks. You have chosen high performance simulator, you have chosen APS, right? The red square over there, APS, and then you said do not override here because in the form you are choosing conservative, moderate, or liberal. So in the main form you are not doing anything. Multi-threading, whatever, but here, down here is enable post layout optimization. So always, if it's a post layout netlist in APS, enable this, and then you get all these post layout optimization choices. Always use HPA for RF, and prior to Spectre 18.1, this would have been the choice, but since none of you are in 18.1, you are in 20.1 or 21.1, use HPA. So this form should explain that. So best practices for RF analyses. So let's kind of go through a few things. I will try and, let's see how to do this. Okay. Oh, okay.
Now it's here.
Oh, now it's here. Okay, great. I will just go back into this mode. Okay, so all of these that I talked about now will make sense because that's where they are in the forms. So remember, I told you I am not going to read anything that is here. You guys can read for yourselves, but I'm just going to talk about the things that will get you, if you don't know. So HB, when you want to run harmonic balance, do not go to the old form, PSS form, which has shooting on the left and HB on the right. Don't go there. Use HB when you want to use HB. Just click on choose analysis, HB, and then the left hand side form is the HB form. You'll get that. And remember, I said we always ask you, will you run transient? Here the option we chose is decide automatically, but there are two other options, yes and no. I would say I would never go for no. I would say yes or decide automatically. If you decide automatically, Spectre will say auto, and then it will come up with the value of t-stab, which is very important for convergence. And if you say yes, because you really know what your t-stab is going to be, we'll ask you to fill that out, the value of t-stab. And then you can have number of tones, you can have so many number of tones, you can have fundamental frequency, all of that. Number of harmonics, this is HB. So number of harmonics, like I wrote down, is very crucial to simulation time and accuracy. You can put it as auto. We did not have auto before, most other vendors didn't. And you had to do trial and error, but auto really will help you get there. Oversample factor. Oversample factor is something that is kind of like, it affects your accuracy and simulation time. If you have very linear, like sinusoid, use 1. If you have rounded edges kind of in your waveform, 2. If you have literally square waves and you are still trying to use HB, use 4. But remember, 1, 2 and 4 come at a price of simulation time. If you do not use anything more than 4, because if you are having to use something more than 4, you shouldn't be using HB, you should be going to PSS or QPSS. So oversample factor will cost you in simulation time, but if you have something that is non-linear and you still want to use HB, 1 is not going to help. You can go to 2 or 4. And then again, you have conservative, moderate and liberal like the others. And then oscillator, if it's an autonomous design, then you will have to click on oscillator and then you'll give the nodes. So this is how HB form works. So again, if you use HB, do not use it from the PSS form. Use it from the HB form.
So I have a question. So if we have two closely spaced tones, is it better to use a small beat frequency and one tone, or is it better to specify two separate tones? So if you look at the number of tones.
Oh, depends. Do you want both to be considered as large tone?
Yes. So let us say I have two large signal tones.
Then 2.
So
then you want 2 with a beat frequency. Yeah. And if they are fairly linear, you can use HB. And if they are not linear, PSS. And dynamic parameter, we talked about that, I think, now to speed up simulation, right? So what does dynamic parameter do? Here again, there is this button called dynamic parameter. If you don't enable it, nothing will happen. It will just be a closed form like it doesn't exist. But if you do enable it, then actually you can define, say at time equals 0 to 100 nano, you will use trap only and reltol 1e minus 3, and then at 100 nano we will change this 100 to wherever. So you can actually change a bunch of things using dynamic parameter, and then that can help you kind of get through, say if your PLL is going to lock at 100 nano or something, from 0 to 60, 70, 80 nano, you really don't care about your accuracy. And if you put conservative all the way, then you're just going to spend so much simulation time for accuracy that you do not need. So, since we are in the business of designing simulators, building simulators, try to get the most out of your simulator by getting the most performance with the accuracy that you need. If you do not need extra accuracy, don't just slow yourself down by using conservative all the time. It doesn't help anyone. So try to get the most out of the simulator. That's what I guess I'm trying to say. And then if you have an oscillator, then of course you will enable oscillator. That's the only way you'll get there. And then you have to give a guess of oscillation frequency, and then what you can do is to come to that oscillation frequency, you can actually choose a design variable and in discrete time steps, so it can go in those time steps to actually get to that oscillation frequency quickly. So these are kind of aids in getting to the oscillation frequency that you are aiming for. Pardon me?
So it can tune like a capacitance or
Yeah,
something
yeah,
like that?
yes,
Like
yes, yeah. So again, I guess this is what I had. Sorry, didn't move. Another thing in HB is XDB compression. So the HB form is very long. You have to keep scrolling down. And the last thing actually is we can calculate XDB compression point for you. Like you can say, this is 1 dB, but you can say 3 dB or 4 dB compression point, and you can, and this is the form. And actually there is, if you want to know the details of how to set it up, I mean, it's pretty much self-explanatory, but if you need more details, just go to support.cadence.com and do XDB compression, HB. If you just kind of, it's like Google for Cadence, you can actually, it'll have some probably example or something. So this is, last but not least, a very big feature actually. I have some working screenshots. So if you say, a lot of our customers are 5G millimeter wave radio people, and they use the 5G NR source, but this is not just for 5G. So if you go to envelope following analysis capability, we have a classic and a wireless. I am kind of going through the highlights of our RF analysis. So I know the previous slide and this slide are not connected, but it'll help you kind of know what we have. So if you use the wireless mode, what we have is we support a lot of standards. I'm not sure if I have the list here, but probably not. So like 802.11a, C, F, I can keep track, but Zigbee, 5G, new radio, all of that. So we have a lot of sources, standards that we support. So suppose you go to wireless, and then all we ask you is actually to fill out this section. That's it. And then conservative, moderate, or liberal. And then what we do is we can plot your EVM, constellation plots, ACPR, power spectral density, all of that. So because we know if you use a 5G NR, it's a parameterized source, so that you obviously have to show which bandwidth, what packet sequence. I don't remember all the parameters, but once you set those parameters and then you say use this to calculate in your design, then you can basically, we calculate all of these for you. But if you do classic and not wireless, you can have your own I and Q files that you can put in, but then we will ask for a lot more information than this, because we do not know the sequence, or because it's not a standard. Then we can calculate your ACPR and power spectral density, but probably not constellation plots and EVM. So I will actually have screenshot of this, so you can. On the setup, do we have questions? Anything? Now we'll go a little bit on multi-threading, multi-core, speed, all of that. So single process multi-core simulation. So here the most commonly used use model is, of course, you use Specter X or APS and you do multi-threading. You say auto or you can say manual. I don't know why I always use manual anyway. And then for post layout, use 8 or 16 threads, and for pre layout you could use 4 or so. And then if you have a job distribution policy, job policy like LSF or something, you can use that. You can say manual and then say LSF, and it works the same for Specter X or APS. And the scaling, as I mentioned last time, is much better in Specter X than APS. Up to 16 is pretty much the same, but after that also in Specter X it's pretty linear up to about 128 threads. And and these numbers are all embedded in the slides. So if you want more information on how multi-threading works, what kind of operations are multi-threaded, what are not, all of those information will be in these articles if you go to support.cadence. By the way, do you guys have support.cadence accounts or? Yeah. Yeah? Okay, great. So that is something actually all our commercial customers use, even our AEs use when we have a doubt. So this is actually very useful. So anyway, so that's what I guess this slide is about. You can use multi-threading or multi-processing. So again, selecting the number of harmonics, I already went through kind of the basic premise of it. So selecting the number of harmonics, use auto harms, and then use the number of harmonics auto, and then if you want to really double check, increase the number of harmonics by 50%, see if it changes the answers or not. But always make sure you use auto. That kind of gets you out of the trial and error phase of trying to figure out the number of harmonics. And number of harmonics versus oversample factor. Like I said, for sinusoids, oversample of 1, rounded edges about 2, and very sharp edges, square waves 4. Try not to use more than 4 because that will really slow down your simulation. So, speed versus accuracy. Again, we talked about rapid IP2 and rapid IP3. So, if you can approximate your second tone to be a small tone, then use rapid IP2, IP3, because then we use one large tone and the other one we approximate it as a small tone. And many customers are quite fine with that and they prefer that because it's faster. Whereas, if you want to do actual IP, actual two-tone IP2, IP3, IP5, you can do that as well. It's your choice. So, how do you set up? How do you set up for rapid IP2 or rapid IP3 is how this form is kind of gives you an idea. You use HBAC or PAC for rapid IP2 and IP3, and this is how you can kind of set up the form. So, we have customers who actually swear by one or the other. They will not use the classic way, the large two-tone IP2, IP3, and there are others who will only use them. I'm not sure why. It's probably a so again, another thing that if our RF designs are really bad about memory always. If you have say P noise with a lot of sidebands, or suppose you have multiple P noise, we allow you to have multiple P noise. So, if you have multiple P noise, whatever the reason may be, you could be using a lot of memory. And so, that for those reasons there is something called using the low mem option, and it's available in HB and also in XDP HB. If you use the multiprocess and HB, it is available, and this is how it actually reduces the memory footprint by about 30% for 3-tone HB. So, it is very, and this is how you get to it. So, here you have low mem equals, so must set here. This is how you set up the low mem option.
What is the trade-off?
The trade, oh, I mean if you do not use it?
No, I mean like,
Yeah.
so nothing is free, right? So like if you use low memory, clearly you're trading something. Is it accuracy? Is it time? Is it?
So, actually, yeah, that's a good question. I do not think there is a big trade-off actually. The thing is, do you really need it? You probably don't need it for everything, but where you are actually struggling with memory issues, then we'd say, because I think all it does is compression. So, it will do an internal compression to reduce your memory footprint. So, here this is how you select in AD Explorer, and I'm hoping you guys will go to Explorer and Assembler, because that's the only way you can access Specter X for RF or for anything or transient. So, simulator, options, analog, and then you go to miscellaneous. Here in the additional arguments, you can actually say HB low mem default 1. So, that way, and then if you want to make sure that your request or whatever was actually taken, then you go into the netlist and it will actually show here in the spectre.out. You'll see a HB low mem default mode equals 1. And there is also something called the memory estimator, and this, without running a simulation, HB will actually estimate how much memory you're going to take and give you some recommendations. And that you can, again from the log file or from the netlist, it will say memory estimate equals yes, and this is how you set it up. And it will not actually run a simulation. Before running a simulation, it's going to tell you what kind of what memory usage it expects, and this is how the log file is going to look. So, again, this is more troubleshooting. If you have trouble with convergence, usually, not always, it's usually AHDL models that can cause the most problem with convergence, especially if you have very fast rise and fall times. If you have very quick transitions, that can really cause a lot of problems, and that's why when there is non-convergence issues, one is of course writing out to the log file, and the other is enabling AHDL linter. That like AHDL linter option, once you enable that, or at least say give a warning, then you will get a lot of warnings if your AHDL model is the culprit. And the other thing that may cause a non-convergence is trapezoidal ringing. If you have, and the thing is, in APS, if you have non-convergence because of trapezoidal ringing, then you can change the method, whereas in Specter X, trapezoidal ringing is detected automatically and they change the method automatically if it's needed. So that is another source of non-convergence. And the other thing is this is like I think I talked about this form before. This is Specter X, and you can choose your preset, choose multi-threading, choose number of options, but if you go to advanced options and enable it, then you will be able to put something in preset override. And in preset override, you can actually force the simulator to take something like preset override method. It will override both the method and the t-step method, and you can actually put in something specific for the simulator to take from an APS netlist, which otherwise it would completely ignore. And when you say advanced options, you can also change the handshake mode of the post layout optimization technique. Is this kind of clear? Is this confusing? Another thing you can do is by introducing CMIN to be able to get convergence, but that can also cause inaccuracies. So you got to be careful just to force convergence. Don't just put in a large CMIN. One way to actually figure out what's going on is to add diagnose, plus diagnose. So what it does is when you actually add plus enable, you can actually do it through the UI as well, enable diagnostic method, yes. So when you put plus diagnose, don't do it all the time. The reason is if you put plus diagnose all the time, it's going to really increase your log file size. I mean, the Spectre log file will be so large that it will give every possible place where there was the time step became small. It's too much information. So unless there is a problem, don't enable plus diagnose. But if there is a problem, it's very helpful. So it will actually give you where your time steps became really small, or where there was, it will turn on AHDL linter. It will give a lot of information. So plus diagnose only if you have a problem. Let's see. Where does it say? So yeah, we talked about diagnose. Pay attention to the spectre.out file. Another thing which is not written here is to give us an internal log file. And how do we give internal log files is this one. So if you set env Spectre report numbers to 1 and then run your simulation, we will actually save an internal log file, which is a binary file which you can send Cadence, and that is actually very helpful for us. And this is kind of a few things I think everyone should know if they are doing Spectre RF. This is not related to the algorithms per se, but these are things that are good to know if you are not aware that we have it. So we have fully featured S parameter analysis with S parameter noise and S probe. Not sure if you guys ever use it, but it's there. And then HB PSS, of course, and then we can do swept HB. We can sweep large tones as well. So suppose you have a PA and you want to see what is the large signal gain of the PA, say over 2 to 3 gig or something, you can sweep the large tone for that. And then we can also do multiple P noise and HB noise. Not sure if you guys are aware, and that is very important when you have different stages of the design and you want to do a P noise at different points, that is very useful. Then you can do one PSS and multiple P noise. So that is useful. And then we have the wireless envelope analysis, and not sure if anyone uses S-probe. So what S-probe does is, when you're doing S-parameter analysis of a design, if you insert S-probes at different points, you can see your S-parameter at those points looking left and looking right. So, but then if you want to go a few hierarchies down in your design, you can use something called deep probe with S-probe. Then you can kind of say, I want 3 levels down and here, stuff like that. But if it is at the top level, it's easier. And these are direct plots and real-time tuning. I just want to show you guys what we have. You know, for me, visual is more important than, you know. So remember I talked about wireless sources and doing envelope analysis with wireless sources like 5G or you know, 802.11a, whatever. So this is how it is. So this used a LTE source, and then as long as you use this wireless probe, what you can, then you can actually specify the source that you are using. It's LTE here, you could do 5G, and then once you run envelope on this, what you're going to get is constellation plots, power spectral density, ACPR. All of these are possible when you use the wireless flow, because then we know it's a standard. If you are giving us your I and Q files, use the classic flow, then we can only give you power spectral density and ACPR, but we cannot give constellation because we really don't know the sequence. And these are all kind of squished together, but I do want to say these are very good to know. If you do add to outputs, always remember that's a button, that's your friend. If you enable add to outputs, what it does is, I'll show you in the next section, it will actually write the equations of all of these in your other pane, you know, in the assembler or explorer pane, and that is very useful because you do not want to type those equations. Definitely I don't, because I always mess up the parentheses and then everything's gone. So you want add to outputs if you want to be able to see the equations of all of these expressions that you have. And then this kind of gives you an idea of, you know, we can do S-parameter analysis, we do HB noise separation, you know, you can see the contribution from each sideband. So there's a lot of things that are available. We just kind of highlighted this. If you're doing RF design, you might want to know these exist. And then something that are good for writing your reports, especially a lot of our commercial customers use it for design reviews, is we have customized plotting templates. You can say, what kind of grid do you want? You can have 3 by 3, 4 by 4, 2 by 2, whatever it is, or you can actually say, I want this one to be stretched over 2 windows because I want my Smith chart in there. So you can have a combination of rectangular and polar and Smith charts, and this is very good for reports. And the other thing is, you can save this grid and this custom template as part of your Maestro view. So when you're in Explorer or Assembler and you're running a simulation, then you say, I want this custom plot, and then you plot it this way, and then you save the Maestro view and you call it My Test 1 or whatever. Next time you open My Test 1, the plotting will be saved because you called it something. And for one Maestro view, you can have even 3 types of plotting templates. Maybe something for trans, something for S parameter, something for harmonic balance. And then each of these can be seen in card mode or in like as one of them, or you can kind of expand to the way it was before. And this is how you choose plotting templates. You can customize your template, you can call it a name. And this is what I meant by add to outputs. When you enable add to outputs, all of these expressions are written here. So you don't have to simulate them all the time, plot them all the time or save them all the time, but they are there if you ever need them. So that is why I think that's very important to know. And then value add, we never had that before. So value what is the expression of this, what is the value of the voltage at harms 1, 2 and 3, or at the time point of 0, 100 picoseconds and 200, or noise type of PM at 100K and 1 meg. So, the value at, I mean, is something that gives you right away as opposed to you hunting it down in the waveform.
Yeah, so it's just a substitute to writing using the value function in the calculator, right?
Yeah, it's available to you through direct plot. That's all. Like Matlab integration, I'm not sure if anyone uses Matlab here integrated, but like I showed you those expression places here. So if you have embedded Matlab expressions here, if you say plot and save there, if you have Matlab licenses, what happens is when we say plot these, those will be, Matlab license will be called and those expressions evaluated and plotted or saved. But of course, you need a Matlab license, it's not from us. But real-time tuning, I'm not sure if anyone is aware this is available. This is available in Explorer. Again, if you want to do something quick, all you have to do is enable real-time tuning. I'll show you, it's one of the buttons at the top, and then you hover over any of your design variables, and you can use a kind of slider, and you can see almost in real time how your AC response changes or any of that. That is of course not a substitute to use say instead of sweeps or something like that, but this is something very quick. We are not going to reevaluate your checks and asserts or do anything like that. It is just very quick way of saying if you're, and you can actually vary multiple of them. If you vary say 3 of them, put a pause, vary 3 and then you unpause it, then you'll see the effect of change of 3. If you just don't pause anything and you just hover over 1 and move, then you'll see the effect of changing 1 of them. So that is something that a lot of our commercial customers liked, and this is where the button is for real-time tuning, and you just move these sliders like I said, and once you move them, and then what happens is it'll hold a Spectre license as long as you are enabling real-time tuning, and it's not a big deal for you guys, but our commercial customers, they want to make sure that the Spectre license is released so someone other user can start to use it.
So each tune is a new simulation, or it runs all of the simulation and actually sees the results based on the values of like.
No, so the thing is, suppose you change C load or whatever I had there. Oh, sorry.
So it's a new netlist.
So the thing is, we just change one value. We are not going to like completely reevaluate expressions, go re-netlist the full thing. It's just going to be very quick, just one small change and so it is not very accurate. You just want to know if you are headed in the right direction or not. It is not meant to replace sweeps or anything like that. It is just to say, well, if I change my load if I increase it, am I in the right direction? It's not accurate. All I'm saying is it just gives you a trend of which way you're going, if it's right or wrong. Not an optimizer, not a.
I know, but
yeah.
My question is like, when I change that value, will it run a new simulation?
Yes, it will run. But the thing is, you do not want to run a simulation that is very time consuming like HB. Then the whole point is lost because it takes a very long time. But if you're doing a quick AC response or a quick SP analysis, it's very useful for quick simulations where time is of essence. If it's HB and it takes like an hour.
But like my question, like
yeah.
actually, like, and I found the answer already. Like, will it run actually new simulation?
Yeah. It will run. It will run.
Iteration is just a new simulation.
New simulation, yes. But the thing is, it will not be accurate where all of the elaboration, evaluation of expressions, checks, nothing will be done. Just a quick re-netlist and simulation. Yeah. So the next few things, actually, I did some sims myself, and I just wanted to show something. So, really do use assembler or explorer. The reason is see this is Maestro, right? So this is Explorer, Virtuoso AD Explorer. See how much more powerful it is from ADL, because here you can actually do corners, Monte Carlo, all of that with a single test bench. You have multiple analysis in a single test bench. And how do you move from Explorer to Assembler? See, there is an upward arrow. If you go to the upward arrow here, you will go from Explorer to Assembler, because Assembler is multi-test bench. If you are in Assembler, there is a downward arrow and you can dive down into any of the test benches. You can have 20, 30 test benches in one Assembler, but this is Explorer, one test bench with the ability to do. Yeah, you had a question?
Yeah.
Sorry.
It's something that's kind of funny. I don't know if this has happened to other people or it just happens in my Cadence setup.
Yeah.
But sometimes when I move down a test in the assembler or I move up, it automatically switches windows to another assembler linked to another schematic.
Oh no, that should not happen at all.
Like the two windows are open. I don't mean the same window switches to another test. What I mean is that both windows are open, but the one where I go down a test or go up to the assembler top level, that window minimizes, and it just goes to the assembler I opened first. That's the one that is maximized and appears to me on the screen. Sometimes it's very confusing because I click run, and it turns out it's not the analysis I want.
Oh wow, yeah, that is odd. I'm just thinking, this is just a guess. I'm not even sure if that's what's happening, but maybe you have something set in the environment variables in your CDSE and V that is maybe causing it. Again, send me these things that you're seeing in my email. I have given you my email. Send it to me. Maybe it's an environment variable, I think, that you said, but it shouldn't, because I run the tools myself. So when you just go up and down, it doesn't go off to another one. No, it's not supposed to. And then here, as you can see in Explorer, you have one test bench, multiple analyses, and see all of these expressions, which I may or may not plot or save. And the thing is, when you have a custom template, here I called it setup_HB4, I could have multiple templates, and then once I run, say, HB, and I swept power, and then I ran some of these values. Since I saved this particular template will keep replotting. So you can actually save a template and reuse it every time, as long as you've saved it. So again, we have large signal, small signal. These are like small signal analyses. Like this time I have used SP, S parameter analysis, and this is how the setup was. And these are like NF, NF min, VSWR. And again, this is another setup, another custom plot like setup SP, SP, S probe. And you can have different types of custom plots, templates. And for each of these analyses, if you do it, then it will appear, and it will always appear in the same grid in the same way that you want. And for RF designers, this is kind of really something they wanted. Again, how does S probe work? So basically, if you have SP and you don't have S probe, no big deal. If you want SP with S probe, you can stick in the S probe, and it's not going to cause any loading. It's just for measurement. It's not going to cause any loading. And then if you want to do a Smith chart, if you want to plot it there, you can select the S probe here, and then you can look at S1, S parameters looking left, looking right at the S probe. And this is the direct plot form for SP with S probe, or you could do just regular S parameter analysis. Again, load stability circles, source stability circles, PAE, output power. Of course, here what I've done is, see, you can combine, you can actually have a custom plotting template combining small signal analysis with large signal analysis, if that's what you want, and you can kind of combine them together as well and save it as a plotting template. Do you guys have a need to do load pool contours for PA design, transmit side? No. So we have the ability to do load pool contours, and you can actually go to Analog Live, and select the port to be a normal port or a harmonic port, and then you can pull the harmonic that you would like, and then you can plot your you can actually pull the harmonic that you like. So you give the resistance and reactance of the other harmonics and you leave that alone, and then you can do load pull contours. So this is how envelope analysis with 5G looked. So any questions? Either I've confused you, put you to sleep, or you are understanding everything. I'm not sure which one it is. I'm hoping it's the last option.
I think a lot of it is that we just need the slides so that, because a lot of things are very specific.
Yes.
That there's no way we're going to remember them.
Yes, of
So
course.
it's kind of we're absorbing the information.
Yes, I
but
understand.
then,
I was
like,
joking.
over the simulation, you're gonna
No, I
need
was
this.
joking.
Yeah.
I used to teach Spectre RF over 2 days, when it was a thing to
Yeah.
actually sit down for 2 days and
Yeah,
do.
like a
So we
whole-
used to do labs. Each of these used to, it was 5-6 years ago, but it used to be a lab. So we actually went through the whole exercise of, rapid IP3 versus real IP3 and setting it all up, setting up the sources. So it's a lot of information. It's like 2-3 days of information in 90 minutes. So that's why it seems like I'm jumping around, but that's why I wanted to write things down just to get a flow, Otherwise, it's like there's HB noise, there's P noise, there's transient noise, there's like all over the place. And the only small signal noise we have is actually, the only large signal noise we have is transient noise. Just remember that. Those are things, that it's not very obvious always. That's the only way to do large signal noise. And if you want to look at noise contributors, run P noise or HB noise and go to PSS noise summary, and then I don't know if everyone knows, then you can do spot noise or integrated noise over a certain range, and then you can say, I want my top 100 or whatever, top 20 contributors. It could be just resistors, it could be all devices, it could be just transistors, doesn't matter. You can choose that, then you can get your top 20, top 50 contributors. But that does not work with transient noise. It only works with small signal noise. So there's a lot of information. It's almost towards the end, but I just want to leave you guys with this. I know Hossein asked about simulating with S parameters. So I would strongly suggest going to, this is actually a 90-minute presentation by one of my colleagues, but this is also available on support.cadence. What are the things to look out for to get best convergence with S parameter files in time domain and in HB, both. But this is very useful, and she has updated it for 21.1 with the latest interpolation methods and all of that. So this can be extremely useful if you are trying to do, if you are trying to bring in large S parameter files and try to simulate with TRAN or PSS or HB actually. Transient as well, because transient is in time domain, so convergence is an issue for S parameters in time domain. So these are some of the fundamentals. You need to have enough data, that's big, down to DC, and data is causal, data is passive, adequate data at high frequency, all of these. So, and there are some debugging, some ways to debug, like the interpolation method, the type of device, and so this is kind of, I think, the latest in the UI. So here, this is what I was talking about. The interpolation method, there's a new one called default. So I would strongly suggest using that. So that way you give us a chance, instead of you saying I want spline, then we are not going to try anything else. But if you say, use default, we can actually use different methods for different parts of the simulation. In fact, if you use PSS, we may use one interpolation method for the transient part and one interpolation method when PSS starts. So those are things you are not able to do if you do it manually.
Is default guaranteed to be the most accurate? In terms of I in the past, for years, I've used PBSpice.
Yeah,
and
yeah.
It seems, in my experience, like having tried all of them, it seems like it's the most it was the most likely to converge, but I think you mentioned the default is something that's somewhat new, and I mean, I haven't.
Yeah, the thing is,
myself.
default gives Spectre the ability to morph between interpolation methods
Okay.
at different points of the simulation. So if we determine BB Spice is what it's going to be, that's what probably it's going to use. But if it needs to change, it will.
Okay.
That's kind of, I think, in my understanding, that's. And then you need to be able to look at your S parameter data. If you get S parameter data, look at it using Viva. Just open up Viva results browser, look at it. And then if you want to compare the simulated S parameter data with S parameter data that you got from somewhere, you can use Viva again to look at both the waveforms and see what's wrong or how close they are or how far off they are. Those are tools that we have that we want people to use for debugging purposes. And then endport compression, and so in order to speed up simulation without actually affecting accuracy, we would like people to use this endport compression. And so this is where the buttons are. And if you guys want more details on why you are doing any of these things, go to that article on 7 habits of highly successful S parameters, because this is just a few slides from that 90-minute presentation. This is actually a 90-minute presentation by itself. So it has like 80, 90 slides on real deep dive into why we are using any of these, and if you're sacrificing accuracy, if you're getting speed, all of these, and every one of these kind of parameters are explained. I'm not going to go into details of that, but feel free to look at that. So these are kind of some of my concluding slides. So I talked about it. Why would I choose PSS over HB? If there's any questions, please ask. And then how? So always when you have multi-tone HB, you can choose auto for tone 1, but we suggest you give the number of harmonics for the remaining tones, 2, 3, whatever, here we have 2 tone. And then if there's a second tone and it produces, if you think it will produce a lot of distortion, use a larger number of harmonics. If you think not, use a smaller number of harmonics for tone 2 in HB. And then I do not have a slide on this, but you can always look at the cut. I don't think a lot of our customers actually use that, but I think under, I don't know where it is, maybe in the options section of HB, there is something where if you have, say, 7 harmonics of tone 1, 5 harmonics of tone 2, so there, if you have a funnel cut or if you have different cuts for harmonics, so basically you do not spend time evaluating the harmonics which are the outliers which have lower energy. You only use the harmonics within that cut. So I can send more information, or you guys can go into support.cadence and look at max IM order or funnel cut or a way to cut harmonics. But I would just use the default, but this is something that's available. Yes?
So can we use auto for both tones if the tones are of equal importance?
Usually I think the recommendation is use auto for the first one, but specify a number for the second one.
And what if for the case of QPSS, when we have like...
QPSS has no auto.
Oh yes.
Yeah,
But
QPSS.
Oh yeah.
Yeah, it does not.
Right.
So in QPSS, you have to specify how many harmonics of any number of tones. And QPSS does not limit how many tones you can have. You can have 5 tones. You can have 7 harmonics of all tones. I mean, whatever. You can have any number of anything, really. It does not limit. And yeah. I would use QPSS when HB is not a possibility and when PSS is not a possibility. I would not dive straight into QPSS unless there are so many tones and all nonlinear and with so many harmonics per tone.
So in case of a mixer simulation with one LO tone and two other large signal tones,
Yeah.
so 3 large signal tones in total, which one should be tone 1? Because the 2 signal tones will cause the most distortion.
Yeah, but if you are going to have 3 large tones, so in a mixer with say LO and 1 RF, you can use, I always use PSS, but with RF and LO. But if you are going to have like 3 large tones at the end of the day, if it is fairly linear, I would use HB.
So, but which one will be tone 1 in that case?
The one that causes the most distortion is going to be tone 1. It's usually the yellow.
Okay.
Yeah. And one thing I want to, just since you brought up mixer, so S parameter analysis is great, but it is good only when there is no frequency translation. When your input and output are at the same frequency, SP is great. But why do we have periodic S parameters like PSP? Or that's because of mixers. If you're going to see your S parameter from LO to RF, because not RF, LO to IF, so your LO is at 1 gig, your RF says at 900 meg, so your IF is at 100 meg. So port 1, port 2 are at different frequencies. That's when you need periodic S parameters, because that will take into account frequency translation. Yeah, I mean, this is not related to this, but since you brought it up, I thought I'd mention. So I think we are at the end, and this is just a recap of what I spoke about. And towards the end, we talk about distributed HB over multiple processes. So if you go to Specter X, and there's multi-thread and multi-process, if you go for multi-process, then you can actually spread one simulation over multiple processes and specify how many, you can do a whole bunch of things. So the thing is, XDP works only for HB, not for PSS. And if there is interest in that, we can always send you more information. So yes, yep, thank you everyone for attending, and you have my email. If you have questions, send me, and I will send these slides as PDF to you guys. Thank you very much. Thanks a lot.